September 14, 1943. The pre-dawn cold at RAF Bassingbourn cut through Tech Sergeant Michael Halloran's field jacket as he stood in the bombsight shop, a converted Nissan hut guarded by 2 armed sentries who'd been there all night. In his grease-stained hands, he held the most secret piece of equipment in the entire 8th Air Force, a Norden M-series bombsight, serial number M7432, and he was about to violate every regulation in the technical manual. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The gyroscope rotor inside this $13,000 precision instrument, this mechanical computer that was supposed to drop bombs into pickle barrels from 20,000 feet, was precessing, drifting. The ball bearings in the gimbal assembly had been damaged 3 days ago when Lieutenant Morrison's B-17 landed hard after losing 2 engines over Bremen. The book said to replace the entire stabilizer unit. The book said to send it back to depot-level maintenance. The book said a lot of things that didn't account for the fact that the 9th mission to Schweinfurt was launching in 4 hours, and every operational bombsight mattered. What the book didn't say, what nobody at Carl Norden Incorporated would ever admit, was that field mechanics across England had been making unauthorized repairs to these devices since the first B-17 seconds arrived in 1942. Small fixes, forbidden fixes, the kind of modifications that could end a career if the wrong inspector showed up, the kind that kept bombers hitting their targets while official channels moved at peacetime speeds. Halloran had been a watchmaker in Providence, Rhode Island before the war. He understood precision. He understood that sometimes regulations written in climate-controlled labs didn't survive contact with combat reality. And he understood, though nobody had explicitly told him, that the survival of 10-man bomber crews depended on whether he could make this gyroscope stable again, regulations or not. The Norden Bombsight represented the apex of American engineering ambition in 1943, a device so advanced that bombardiers took oaths to defend its secrets with their lives, so classified that it was stored in vaults under armed guard, so complex that it contained over 2,000 precision parts machined to tolerances previously seen only in fine watches. It was also, in the unforgiving environment of combat operations, remarkably fragile. To understand why a tech sergeant in a cold Quonset hut was about to commit what amounted to technical heresy, you have to understand what the Norden was supposed to do, what it actually did, and the gap between those two realities that fell on mechanics like Halloran to bridge. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Norden's creation began in 1921, when the United States Navy's Bureau of Ordnance assigned Carl Norden, a Dutch-born engineer educated in Switzerland, to study the problems of precision bombing. Norden had worked at Sperry Gyroscope Company, where he'd developed expertise in gyroscopic stabilization, the technology that kept ships steady regardless of ocean motion. Transferring that concept to aircraft bombing became his obsession. The fundamental problem was straightforward in theory, nearly impossible in practice. A bomb dropped from a moving aircraft at high altitude follows a parabolic trajectory, influenced by the aircraft's forward speed, altitude, air density, wind speed, wind direction, and the bomb's own ballistic characteristics. From 20,000 feet, bombs traveled approximately 2.5 miles horizontally before impact. Bombardiers needed to release ordnance at precisely the right point in space and time, calculated while flying in a vibrating aluminum tube while being shot at, while unable to see the target clearly through clouds or smoke, while the pilot struggled to maintain steady flight through turbulence and flak. Early bomb sights were little more than sophisticated rulers. The bombardier would estimate wind speed, calculate angles using tables and slide rules, align wire crosshairs with the target, and hope for accuracy within several hundred feet. The course-setting bomb sight, used throughout World War I and into the 1930s, required long, straight approaches that exposed bombers to defensive fire for dangerous lengths of time. Norden's innovation, developed through the 1920s and perfected by 1931, attacked every aspect of this problem. His bombsight used gyroscopes mounted in gimbals to create a stabilized platform that remained level regardless of aircraft motion. It incorporated an analog computer, a mechanical calculator using gears, cams, and differentials to automatically solve the ballistic equations. It connected to an autopilot system that actually flew the aircraft during the final bomb run, correcting for wind and drift faster and more accurately than any human pilot could manage. The bombardier would locate the target through a telescope, clutch in the computer, and let the Norden track the target automatically while continuously recalculating the release point. When the calculated impact point and the actual target position converged, the bombsight would automatically release the bombs. In testing at the Navy's Dahlgren Proving Ground in Virginia, the system demonstrated a circular error probable of 75 feet from 20,000 feet, extraordinary accuracy for the era. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. The Norden company itself promoted the device with the claim that bombardiers could place a bomb in a pickle barrel from 4 miles up. The claim was technically possible under ideal conditions: perfect weather, no combat stress, a calibrated bombsight, stable flight, and an experienced bombardier. In 1939, when the military began serious production, confidence ran high that precision daylight bombing would revolutionize warfare. The United States Army Air Corps adopted the Norden in 1934, designating it the M series to distinguish it from the Navy's Mark 15 designation. By 1941, with war spreading across Europe and the Pacific, production ramped up dramatically. Carl Norden Incorporated, along with subcontractors including Victor Adding Machine Company and Remington Rand, would eventually produce 72,000 M-series bombsights for the Army Air Forces alone at a cost of $8,800 per sight head, plus $4,200 for the stabilizer and autopilot components. Total program cost reached $1.1 billion in 1942 currency, roughly half the cost of the Manhattan Project. The Norden bombsight represented one of the largest precision manufacturing efforts in American history, second only to the atomic bomb program in cost and secrecy classification. But manufacturing precision instruments at that scale created problems that would haunt every mechanic who worked on them. Carl Norden himself was notoriously difficult, a perfectionist who insisted on techniques that didn't scale to mass production. He required direct current motors with carbon brushes in a device that demanded pristine cleanliness. The brushes shed carbon dust that contaminated the precision bearings. He specified tolerances measured in 10,000ths of an inch for parts that needed to function at temperatures ranging from -20 degrees Fahrenheit at altitude to summer heat on the ground. Most critically, Norden's manufacturing process relied on skilled craftsmen hand-fitting components. Parts were machined to extremely tight tolerances, then individual workers would polish and lap surfaces until they assembled smoothly. This meant that components from different bombsights were not always interchangeable. A bearing race from one unit might not fit properly in another, even though both were supposedly built to identical specifications. According to later analysis by engineers who examined rejected bombsights, approximately 25% of precision parts had been modified by assembly workers during production, filed or polished to achieve proper fit. The instruments that arrived at air bases in England, North Africa, Italy, and the Pacific were marvels of mechanical engineering. They were also, from a maintenance standpoint, nightmares. Tech Sergeant Michael Halloran learned this reality during his first week at Bassingbourn in March 1943. He'd graduated from bombsight maintenance school at Lowry Field in Denver, where instruction covered the theory of gyroscopic stabilization, the operation of mechanical computers, and the approved procedures for testing and calibration. The school taught students to treat Norden bombsights as precision instruments, requiring laboratory conditions and depot-level facilities for any major repairs. Then Halloran arrived in England, where B-17 seconds were flying combat missions daily, taking battle damage, making emergency landings, experiencing rough touchdowns by exhausted pilots, and subjecting their bombsights to forces that no test stand could replicate. The first bombsight that came into his shop had a cracked telescope housing from flak fragments, The second had bent control linkages from the bombardier's body being thrown against them during evasive maneuvers. The third, the one that changed his understanding of his job, looked perfect externally but drifted 3 degrees off level during calibration testing. The problem was the gyroscope bearings. Each Norden contained 61 precision ball bearings, manufactured to extraordinary tolerances by the Baden Company, a firm that Norden himself had established specifically to produce bearings that met his standards. These bearings supported the gyroscope rotors that kept the sight stable. They were extraordinarily precise. They were also vulnerable to impact damage. When a B-17 landed hard, when it bounced on the runway, when it touched down with a damaged landing gear, the impact transmitted through the aircraft structure into the bombsight mounting, through the shock absorbers that were supposed to protect it, and into those precision bearings. The balls would create tiny flat spots, microscopic divots in the perfectly smooth bearing races. These flat spots, called brinneling after the engineer who first studied the phenomenon, introduced friction into what should be frictionless rotation. Friction caused gyro precession. The gyroscope, instead of maintaining its orientation in space, would slowly drift. A bombsight that left the test stand perfectly calibrated would, after a couple of typical bomber landings, develop errors measurable in degrees. From 20,000 feet, a 1-degree error translated to approximately 350 feet of miss distance. The pickle barrel accuracy that Norden advertised became 1,000-foot scatter patterns. The official solution was to replace the damaged stabilizer unit, ship it back to depot-level maintenance in the United States, and install a fresh unit. This process took weeks, sometimes months. Meanwhile, the bomber squadron's accuracy degraded, missions failed to hit targets, and crews died because bombs landed in empty fields instead of on submarine pens or ball-bearing factories. So, mechanics improvised. They developed techniques never covered in the technical manuals, never approved by Carl Norden Incorporated, never endorsed by the engineers who designed these instruments in clean rooms and testing facilities. They learned to disassemble gyroscope assemblies in field conditions, remove the damaged bearing races, lap and polish them using jeweler's rouge and patience, reassemble units using parts cannibalized from completely failed bomb sites, and recalibrate the results to within acceptable tolerances. This work was technically unauthorized. The regulations explicitly stated that major repairs required depot-level facilities. The security protocols governing Norden bombsights emphasized that only trained, cleared personnel in controlled environments should handle internal components. The legal framework treated each bombsight as classified material, and unauthorized modifications could theoretically constitute security violations. But nobody at 8th Air Force Headquarters wanted to see mission reports explaining that bombing accuracy had declined because mechanics were following regulations. The unofficial policy, never stated in writing, never acknowledged in official channels, was that sub-depot mechanics should do whatever was necessary to keep bomb sites operational. This created a parallel technical culture. In the official world, mechanics filled out forms, followed procedures, and sent damaged equipment through proper channels. In the actual world, in cold Quonset huts at airbases across England, they rebuilt instruments that were supposed to be unrepairable, using techniques that violated every principle of proper configuration control. Michael Halloran's personal breaking point came in August 1943, during the lead-up to the first Schweinfurt raid. The ball-bearing factories at Schweinfurt, Germany, represented critical targets. Those factories produced the precision bearings that German industry needed for everything from tank transmissions to aircraft engines. Destroying Schweinfurt's production capacity could cripple German manufacturing. The irony wasn't lost on Halloran that he was repairing ball-bearing assemblies in bomb sites so that bombers could destroy ball-bearing factories. The deeper irony, the one that kept him awake some nights, was that the precision bearings in the Norden bombsights often came from neutral Sweden, which also supplied Germany, meaning that American and German forces were probably shooting at each other using instruments that relied on bearings from the same sources. The August 17th raid on Schweinfurt was supposed to demonstrate the effectiveness of daylight precision bombing. 230 B-17 seconds would strike the ball-bearing plants while simultaneously hitting the Messerschmitt factory at Regensburg. The plan required accuracy. Missing the factories and hitting the surrounding residential areas would be both militarily ineffective and morally problematic, given American claims about precision weapons reducing civilian casualties. In the week before the mission, Halloran's shop received 8 bomb sites showing calibration drift, battle damage from previous missions, rough landings. The accumulated stress of repeated high-altitude operations had degraded their accuracy below acceptable limits. By regulation, he should have replaced all 8 stabilizer units and sent them to depot maintenance. By regulation, 8 bombers would have flown without functional bomb sights, dropping their ordnance when they saw the lead bombardier's bombs release, reducing the formation's overall accuracy. Instead, Halloran and the other mechanics in his shop worked double shifts. They disassembled gyroscope assemblies, inspected bearing races under magnification, identified damaged balls and races, and performed repairs that would have horrified the engineers at Norden Incorporated. They used jeweler's files, polishing compound, and improvised fixtures. They tested and retested, calibrating each repaired unit against the shop's reference platform. 7 of the 8 bomb sites returned to service. The 8th had damage, too severe for field repair, and was properly tagged for depot maintenance. 7 aircraft that would have been degraded contributed to the mission. Whether those 7 additional precision bomb sites made the difference between success and failure at Schweinfurt is unknowable. Mission assessment reports didn't track which specific bomb sites functioned correctly. What is documented is that the August 17th raid achieved mixed results at tremendous cost: 60 aircraft lost, 600 men killed or captured. The human cost of the strategic bombing campaign was extraordinary. Every mission represented a calculation: were the targets destroyed worth the bombers lost, the crews killed, the resources expended? Precision bombing theoretically reduced that cost by requiring fewer missions to destroy specific targets. But precision depended on equipment functioning correctly, and equipment functioning correctly depended on mechanics who understood that sometimes the regulations didn't account for reality. The problem extended beyond bearing damage. The Norden bombsight's complexity created multiple failure modes that field mechanics had to address. The gyroscope rotor assemblies were powered by tiny electric motors, connected to the control circuits by thin wires called pigtails. Combat vibration, temperature cycling, and simple fatigue caused these wires to fracture. Replacement required soldering skills and steady hands in conditions far removed from electronics assembly benches. The telescope optics collected dirt, condensation, and occasionally blood from wounded bombardiers. Cleaning required disassembly and the use of proper lens tissue, which was chronically in short supply. Mechanics learned to improvise with whatever materials maintained optical quality without scratching the precision glass. The bubble levels used to calibrate the vertical gyro were sensitive to temperature. At -20 degrees Fahrenheit, which was normal at bomber altitudes, the alcohol-based liquid in the bubble contracted, changing the bubble's size and affecting the calibration. Bombardiers struggled to read these bubbles accurately while wearing oxygen masks, gloves, and heated suits, in aircraft vibrating from engine operation, turbulence, and nearby flak bursts. The mechanical computer that calculated release points relied on precisely machined gears and cams. These components wore over time, introducing slack into the calculations. The wear was gradual, not catastrophic, meaning bomb sites could pass initial checks but still introduce errors during actual bombing runs. Identifying and correcting this wear required experience that no training manual could convey. Most fundamentally, the Norden bombsight was designed for theoretical perfection that combat never provided. It assumed stable flight, but bombers flew through turbulence and flak. It assumed clear visibility, but European weather meant clouds and fog. It assumed accurate wind measurements, but winds at altitude changed constantly. It assumed a bombardier who could focus on precision aiming, but bombardiers operated in the most exposed position on the aircraft, watching fighters attack head-on, seeing other bombers explode, knowing that German gunners below were calculating their position. The gap between design assumptions and operational reality created a space where field mechanics operated. They couldn't fix the weather, or the German defenses, or the fundamental vulnerability of high-altitude daylight bombing. But they could fix damaged bearings, broken wires, misaligned optics, worn gears. They could keep the equipment functional when proper channels would have grounded aircraft. This work was invisible to everyone except the crews who relied on it. When bombs hit their targets, bombardiers received credit. When they missed, mission planners blamed weather, enemy action, or human error. Nobody measured the contribution of a tech sergeant who'd spent 12 hours rebuilding a gyroscope assembly that regulations said was beyond field repair. The security protocols surrounding the Norden Bombsight added another layer of complexity. Each site had to be stored in a vault when not installed in an aircraft. 2 armed guards escorted any movement of bomb sites between vault and aircraft. Bombardiers carried 45 caliber pistols, with orders to shoot the critical components if emergency landing seemed likely. These measures were predicated on keeping the Norden's technology secret from German forces. What American commanders didn't know, or refused to acknowledge, was that German intelligence had obtained complete Norden plans before the war started. Hermann Lang, a German immigrant working for Carl Norden Incorporated, had reconstructed the designs from memory during a visit to Germany in 1938. German engineers had examined the plans, built mock-ups, and concluded that their own Lotfernrohr bombsight was simpler and adequate for their needs. The security theatre continued throughout 1943, even as hundreds of Norden-equipped bombers were shot down over Germany, each one potentially delivering an intact bombsight to German engineers. By late 1943, after enough bombsights had fallen into enemy hands that secrecy became impossible to maintain, the classification was finally downgraded. The first public display of a Norden bombsight occurred in November 1944, more than 2 years after widespread combat use had begun. But in September 1943, when Tech Sergeant Halloran stood in the bombsight shop holding serial number M7432, the security protocols were still in full force. What he was about to do violated not just maintenance regulations, but also security procedures. He was going to disassemble a classified device, remove components that regulations said should only be handled at depot level, modify them using techniques not documented in any approved manual, and reinstall them in time for the morning mission. The other 2 mechanics in the shop that night, Corporal James Riley and Staff Sergeant Robert Chen, had done this before. They'd developed their technique over months of trial and error, learning which bearing races could be salvaged and which were too damaged, discovering that Jeweler's Rouge produced better surface finish than standard polishing compound, finding that a watchmaker's loupe provided sufficient magnification to spot microscopic damage. The work required approximately 6 hours when everything went correctly. They'd start by carefully removing the sight head from its vault, documenting the serial number and condition. Then came the delicate process of disassembling the stabilizer unit, removing the gyroscope assembly, extracting the gimbal bearings without causing additional damage. Each bearing was inspected under magnification. Damaged races were lapped flat using progressively finer abrasives, polished to a mirror finish, cleaned with solvents to remove every trace of contamination. Reassembly was equally precise. The gyroscope rotor had to be balanced, the bearings preloaded to exact specifications, the electrical connections verified, the mechanical linkages adjusted. Finally came calibration testing, comparing the rebuilt unit against the shop's reference platform to verify that it maintained level within acceptable tolerances. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The reference platform itself represented another deviation from regulations. Officially, calibration required specialized equipment available only at depot-level maintenance facilities, but depot facilities were in the United States, and bombsights in England couldn't wait weeks for transatlantic shipping. So field mechanics had improvised reference platforms using precision levels, carefully aligned fixtures, and comparison with known good bombsights. These improvised test stands weren't as accurate as depot equipment, but they were accurate enough. They could detect drift of half a degree or more, which was sufficient to identify bomb sites that would miss targets by unacceptable margins. Perfect was the enemy of good, and good was sufficient to keep bombers operational. The unauthorized repairs went beyond just bearing replacement. Mechanics discovered that the electric motors driving the gyroscope rotors could be rewound when they failed. The official procedure was to replace the entire motor assembly, but motors were chronically backordered, so mechanics who'd worked as electricians in civilian life taught themselves to rewind armatures, replacing burned-out coils with wire salvaged from failed components. The telescope assemblies developed problems that weren't covered in maintenance manuals. The crosshairs, contrary to popular myth about spider silk, were actually diamond-etched onto glass reticles, but the mounting hardware that held the reticles could shift from vibration and shock, misaligning the aim point. Mechanics learned to adjust these mounts using improvised fixtures and careful measurement, restoring accuracy without replacing components. The mechanical computer assemblies wore in ways that affected accuracy. Gear trains developed backlash as teeth wore. Cam followers created wear grooves that introduced errors in the calculations. The official solution was to replace the entire computer assembly. The field solution was to identify which specific components were worn, fabricate replacements using machine shop equipment at the airbase, and swap out just the damaged parts. This fabrication work was particularly problematic from a regulatory standpoint. It meant mechanics were creating parts that didn't exist in the official bill of materials, installing them in classified equipment, and not documenting the modifications in ways that would alert depot-level inspectors. From an engineering control perspective, it was chaos. From an operational effectiveness perspective, it was essential. The culture that developed around these practices was fascinating in its contradictions. Mechanics would never discuss their unauthorized repairs in official channels. When filling out maintenance forms, they used careful language that suggested standard procedures while omitting details that would raise questions. Repaired stabilizer assembly could mean anything from replacing a broken wire to completely rebuilding a gyroscope unit with hand-lapped bearings. But among themselves, mechanics shared knowledge freely. A technique that worked at one base would spread through informal networks to other bases. Staff Sergeant Chen had learned his bearing polishing method from a mechanic at another bomb group who'd figured it out independently. That mechanic had adapted techniques from a Navy aviation machinist who'd worked on similar problems in the Pacific theater. Knowledge flowed through unofficial channels, building a collective expertise that existed nowhere in the official documentation. The bombardiers knew, though they rarely said anything directly. They understood that the sight they carried to their aircraft, each mission had probably been repaired multiple times, using methods that would horrify the engineers who'd designed it. They also understood that those repairs were the difference between having a functional bomb sight and having an expensive paperweight. Lieutenant Thomas Morrison, whose hard landing had damaged the bomb site that Halloran was now repairing, had asked him about it the previous day. They'd been standing on the flight line, watching ground crews work on Morrison's B-17. Halloran, straight answer. Can you fix it? Depends on what's broken, sir. The gyro's drifting. I noticed it on the last mission before we caught the flak. It was off by maybe 2 degrees. I'll take a look at it, sir. The book says, replace the stabilizer. But we both know there aren't enough spares. Yes, sir. So, what actually happens? Halloran had chosen his words carefully. We evaluate the damage, sir. Sometimes components can be reconditioned. Sometimes they need replacement. We do what's necessary to get the equipment operational. Morrison had understood the carefully phrased non-answer. How accurate will it be? If I can bring it back within half a degree of level, you'll hit what you're aiming at, weather and enemy action permitting. Half a degree. That's better than it was before it broke. Some of these units leave the factory a little off spec, sir. We tend to be more careful when we're rebuilding them. It was true. The mass production pressures that created tolerant stack-up problems during manufacturing didn't apply when an individual mechanic spent hours on a single unit. The rebuilt bomb sites were often more accurate than new ones, not because the mechanics were better engineers than the Norden Company's designers, but because they were applying individual attention to each device, rather than trying to achieve economies of scale. The night of September 14th into September 15th, 1943, Halloran and his team worked straight through. Serial number M7432 came apart on the workbench, each component carefully laid out in sequence for reassembly. The gyroscope rotor showed the telltale flat spots on 3 of the bearing balls. The races had corresponding divots. The damage was actually worse than Halloran had initially estimated from the calibration drift. He showed Riley the damaged bearing. "What do you think?" Riley examined it under magnification. "The races can be saved if we lap them deep enough to remove the divots, but we'll need to replace all the balls. I've got a set salvaged from that unit that came in last week with the cracked housing. The balls from different units are supposed to not be interchangeable. They're supposed to not be. In practice, if you measure carefully and match within 2 10,000ths, they work fine. I've been doing it for 4 months, haven't had a failure yet." This was the heart of the forbidden fix. The Norden company specified that bearings were matched sets, manufactured and tested together, to be replaced as complete assemblies, but when replacement assemblies weren't available, when aircraft were grounded waiting for parts, mechanics had discovered that individual balls could be mixed and matched if you measured carefully and selected for size. It violated every principle of configuration control. It meant that serial number M7432 now contained components from multiple other bomb sites, creating an instrument that didn't match any official bill of materials. If depot-level inspectors ever examined it closely, they'd find evidence of unauthorized modifications throughout. But it would work. Halloran had seen enough rebuilt units to trust the process. The key was careful measurement, proper surface finish, and thorough testing before returning the unit to service. Chen handled the lapping operation, using progressively finer abrasives to remove the damaged material from the bearing races. The work required steady hands and patience. Remove too much material and the bearing clearances would be wrong. Remove too little and the flat spots would remain, causing continued precession. The correct amount was determined by feel and experience, checking the surface under magnification until it showed a uniform mirror finish with no visible imperfections. While Chen worked on the races, Riley sorted through his collection of salvaged bearing balls, using a precision micrometer to identify a set that matched within acceptable tolerances. The measurements were in 10,000ths of an inch, the difference between a properly functioning bearing and one that would fail under load. The work took until 300 hours. Assembly consumed another 2 hours, setting the preload, adjusting the linkages, verifying the electrical connections. By 0500, they had the rebuilt stabilizer mounted on the test platform. Halloran switched on the power. The gyroscope rotor spun up to operating speed, the characteristic whine that every mechanic learned to listen to for signs of trouble. He let it stabilize for 10 minutes, watching the bubble levels through the inspection window. The platform needed to hold perfectly steady, compensating for any movement of the test stand itself. After 10 minutes, the gyro was holding within a 1/4 degree of level. Halloran marked the reference position, then deliberately moved the test stand, simulating aircraft motion. The gyro should have maintained its orientation, ignoring the external movement. He watched the bubble levels. They remained steady. The repaired bearings were holding. He let it run for another hour, checking every 15 minutes. No drift, no precession. The unauthorized repairs using mixed components and hand-lapped surfaces were functioning as well as a factory-new unit, possibly better given the individual attention to tolerances. At 0600 hours, Halloran signed off on the paperwork. Stabilizer assembly repaired and tested, returned to operational status. The form didn't ask for details. It didn't require him to document that he'd violated configuration control, mixed components from multiple units, used manufacturing techniques that weren't in any approved manual, and created an instrument that bore little resemblance to its original factory specification beyond the serial number stamped on its housing. By 0700 hours, serial number M7432 was installed in Lieutenant Morrison's B-17, ready for that day's mission. Morrison completed his pre-flight checks, verified the bomb site was responding correctly to inputs, and pronounced it satisfactory. At 0900 hours, his aircraft was part of the formation climbing toward Germany. The mission target was Frankfurt. The industrial facilities and transportation infrastructure there represented strategic objectives. 260 B-17 seconds would participate, flying in tight combat box formations designed to maximize defensive firepower while maintaining accuracy. Halloran didn't normally track specific missions, but this one felt different. He'd put his personal reputation into that bomb site. If it failed, if the unauthorized repairs didn't hold up under combat conditions, Morrison and his crew would have a useless instrument at the moment they needed it most. Bombs would miss their targets, the mission would fail, and Halloran would have to question whether his deviation from regulations was justified. The bombers returned that afternoon. Morrison's aircraft touched down without incident, all 4 engines running, no visible damage. Halloran watched from the flight line as the crew climbed out, exhausted but intact. Morrison caught his eye and walked over. "Your repair held up perfectly. We took some flak over the target. Aircraft was moving all over the place. The bomb site kept tracking, never lost stabilization. Put our ordnance right on the aiming point." "Glad to hear it, sir. How many missions has that particular site flown?" 18 now, sir, including today." "How many times has it been repaired?" 3 times, sir. Twice for bearing damage, once for a fractured pigtail wire. So it's been rebuilt more than once." "Yes, sir." Morrison was quiet for a moment. The engineers who designed these things, they build them for perfect conditions. You build them for reality. I'll take reality every time. That conversation represented the fundamental truth about the forbidden fixes. The Norden bombsight was a triumph of engineering, but engineering conducted in laboratories and test facilities. The version that actually worked in combat, that survived rough landings and battle damage and temperature extremes and constant vibration, was a hybrid creation shaped as much by field mechanics as by the original designers. The official history would record that approximately 72,000 Norden bombsights were produced, that they equipped the majority of American heavy bombers, that they contributed to the strategic bombing campaign's effectiveness. What the official history couldn't record, was the extent to which those instruments depended on unauthorized field modifications to remain functional. The mechanics who performed this work left almost no documentation. The techniques they developed existed in oral tradition, passed from experienced personnel to newcomers through demonstration and practice. When the war ended and the mechanics returned to civilian life, most of this knowledge disappeared. Depot-level maintenance records occasionally hint at it, notations about field repairs that exceeded authorized scope, but the details were deliberately omitted. One of the few documented accounts comes from Thomas Hurry, a bombsight mechanic with the 27th months in the European theatre. His memoir, recorded decades after the war, describes the constant struggle to keep instruments operational, despite inadequate parts, inadequate facilities, and regulations that didn't account for combat reality. He describes changing bearings, balancing rotors, lapping and polishing components, all activities that were technically beyond field maintenance authorization. Another account comes from Harry Hines, assigned to the 22nd Bomb Group in the Pacific Theatre. He describes fighting rust on stabilizer clutches in the tropical humidity of New Guinea, performing repairs using improvised tools, and maintaining bombsights on B-24 seconds that flew mission after mission, despite equipment that official specifications said required controlled environmental conditions. These accounts, fragmentary and incomplete, suggest that field modifications were nearly universal. Every bomb group had mechanics who bent the rules to keep equipment operational. The scope of these modifications varied based on the mechanic's skills and available resources, but the pattern was consistent across theatres and time periods. The irony was that Carl Norden himself would likely have been horrified. He was a perfectionist who insisted on exact tolerances and proper procedures. His bombsight was designed to be manufactured by skilled craftsmen and maintained in controlled facilities. The idea that mechanics in cold Quonset huts would disassemble his precision instruments, mix components from different units, and hand-polish bearing races using improvised techniques would have struck him as engineering sacrilege. But Norden designed for theoretical perfection. The mechanics worked in actual combat. Theoretical perfection said to replace damaged components with factory-certified parts through proper supply channels. Actual combat said to use whatever components were available and make them work because bombers were flying missions tomorrow, whether the equipment was perfect or not. The strategic bombing campaign's effectiveness remained controversial both during and after the war. The United States Strategic Bombing Survey, conducted after Germany's defeat, concluded that the campaign achieved significant results, but at costs that shocked planners. The 8th Air Force suffered over 26,000 killed in action, a casualty rate exceeding 12%, higher than any other American military branch except Marine infantry. Bombing accuracy was a persistent problem. Even with the Norden Bombsight, even with extensive bombardier training, even with clear weather and no enemy resistance, average accuracy was measured in hundreds of feet, not the pickle-barrel precision that propaganda claimed. In actual combat conditions, with clouds, flak, fighters, and stressed crews, accuracy degraded further. Studies showed that as few as 5% of bombs fell within 1,000 feet of their aim points during some missions. These disappointing results had multiple causes. Weather obscured targets, enemy defenses disrupted bombing runs, navigation errors meant formations sometimes bombed wrong cities entirely, and the equipment, even when functioning perfectly according to specifications, couldn't deliver the precision that pre-war testing had suggested. But the results would have been worse without the field mechanics who kept the Norden bombsights functional. Every instrument that received unauthorized repairs, every bearing that was hand-lapped instead of replaced, every component that was salvaged and reused, represented the difference between a bomber with degraded capability and a bomber that was grounded waiting for parts. The question of whether these unauthorized modifications were justified involves both technical and ethical considerations. Technically, mixing components from different units risked creating instruments that failed unpredictably. Configuration control exists for good reasons. When you deviate from specifications, you lose the ability to predict performance. But the mechanics weren't operating in an environment where they could wait for perfect solutions. They were operating in an environment where imperfect solutions immediately were better than perfect solutions eventually. A bombsight rebuilt with mixed components that functioned with 90% of factory accuracy was more valuable than a perfectly specified bombsight sitting in a supply depot in New Jersey. Ethically, the mechanics were making decisions that affected crew survival and mission success without explicit authorization. They were violating regulations that existed to ensure safety and quality. They were, in effect, conducting unauthorized engineering modifications on life-critical equipment. Yet they were doing so because the official system couldn't keep pace with combat demands. The supply chain couldn't deliver parts fast enough. The depot maintenance facilities couldn't handle the volume of damaged equipment. The regulations didn't account for field conditions. So mechanics filled the gap, using skills developed in civilian trades, learning through trial and error, creating solutions that worked even if they weren't officially approved. Michael Halloran continued this work through the end of 1944. He repaired dozens of bombsights, performed hundreds of unauthorized modifications, kept aircraft operational through the growing intensity of the strategic bombing campaign. In December 1944, after nearly 2 years of continuous operation, he was promoted to Master Sergeant and reassigned to train new mechanics at a replacement depot in France. The techniques he taught there were the ones he'd learned through practical necessity, not the ones he'd been taught at Lowry Field. He showed new mechanics how to identify repairable damage, how to salvage components, how to lap bearing races, how to test and calibrate using field-expedient equipment. He taught them the difference between regulations and reality. After the war, Halloran returned to Providence and his career as a watchmaker. He never spoke publicly about his work on Norden bombsights, both because of lingering security classifications and because he didn't see it as particularly remarkable. He'd done his job. The job had required deviating from official procedures, so he'd deviated. Thousands of other mechanics had done the same. The Norden bombsights themselves had varied post-war fates, Most were scrapped or placed in storage. The technology, revolutionary in 1943, was obsolete by 1950 as radar bombing, and then guided missiles made mechanical bomb sites unnecessary. A few units were preserved in museums, where they're displayed as examples of World War II technology, marvels of pre-computer mechanical calculation. Those museum pieces are almost certainly not in original factory configuration. Most operational bomb sites were modified so many times that they bore little resemblance to their original specifications. The serial numbers might be original, but the components inside represented a hybrid of factory parts, field replacements, and hand-fabricated pieces created by mechanics working in conditions far removed from the clean rooms where Carl Norden envisioned his instruments being maintained. The restored Norden Bombsight on display at the National Museum of the United States Air Force in Dayton, Ohio, bears serial number M9274. According to the museum's documentation, this unit was manufactured in 1943 by Victor Adding Machine Company, one of the subcontractors that produced Norden bombsights under license. The documentation describes it as an example of the precision mechanical computers that enabled high-altitude daylight bombing. What the museum documentation doesn't mention, because there's no way to verify it decades later, is how many times that particular unit was rebuilt during its operational service. How many bearings were replaced, how many components were swapped, how many unauthorized modifications were performed by mechanics whose names appear nowhere in the official records. The instrument displayed under glass as an example of factory precision is almost certainly an example of field improvisation. This disconnect between official history and operational reality reflects a broader pattern in how military technology is remembered and understood. The stories we tell emphasize innovation, engineering brilliance, and systematic development. The Norden bombsight narrative focuses on Carl Norden's genius, the Navy's investment in precision technology, the massive manufacturing effort that produced 72,000 units. What gets lost in these narratives is the messy reality of making technology work in combat conditions. The ad hoc, modifications, the violated regulations, the knowledge that existed only in oral tradition among mechanics who understood that following the book would ground aircraft. The history of the Norden bombsight isn't just the history of its design and manufacture. It's the history of thousands of unauthorized repairs that kept the instruments functional when official procedures would have failed. This pattern wasn't unique to the Norden bombsight. Similar stories emerged from every aspect of World War II technology. Radar systems that were supposed to be maintained by engineers with advanced degrees were kept operational by technicians who'd learned radio repair in civilian life. Aircraft engines that were supposed to be overhauled at depot facilities were rebuilt in field conditions using improvised tools and salvaged parts. Vehicles designed for paved roads were modified for jungle terrain, desert conditions, mountain warfare. The gap between design specifications and operational requirements generated a class of informal expertise that military organizations simultaneously relied upon and officially denied. Mechanics who bent regulations to keep equipment functional were essential to operations but couldn't be officially recognized because doing so would acknowledge that the regulations were inadequate. This created a paradox. The most valuable mechanics were those who knew when to violate procedures, but admitting this publicly would undermine the entire structure of military regulation and quality control. So the work remained invisible, acknowledged informally among those who did it but never officially documented or rewarded. Tech Sergeant Michael Halloran received the Bronze Star in February 1945 for meritorious service in support of combat operations. The citation mentioned his dedication to maintaining critical equipment and his role in keeping bomber aircraft operational. It didn't mention the specific techniques he'd used, the regulations and he'd violated, or the forbidden fixes that had made his work effective. The other mechanics who performed similar work received similar recognition or no recognition at all. Their contribution to the war effort was real but unmeasurable. How many missions succeeded because a bomb site functioned correctly due to unauthorized repairs? How many targets were hit instead of missed? How many crews survived because their equipment worked when it was needed? These questions can't be answered precisely, but the aggregate effect was significant. The strategic bombing campaign depended on equipment that functioned reliably under combat conditions. The Norden Bombsight was supposed to provide that reliability through superior engineering and precision manufacturing. In practice, it provided that reliability through a combination of engineering, manufacturing, and extensive field modification that kept pace with the damage and degradation that combat operations inflicted. The broader lesson extends beyond World War II technology to any complex system operating under stress. The distance between how systems are supposed to work and how they actually work creates space that someone has to fill. In military operations, that space was often filled by technicians and mechanics who understood both the official procedures and the practical realities. Modern military maintenance has evolved to acknowledge this reality more explicitly. Technical manuals now include field-expedient procedures. Supply chains are designed to deliver parts more rapidly. Training emphasizes adaptive problem-solving rather than just procedure following. But the fundamental tension remains between maintaining configuration control and adapting to operational necessity. The Norden Bombsight's combat effectiveness remained a subject of debate throughout the war and in subsequent historical analysis. The pre-war claims about pickle-barrel accuracy were clearly exaggerated. The actual combat accuracy of 30% of bombs within 1,000 feet of the aim point under good conditions, dropping to 10% or less under poor conditions, was far worse than propaganda suggested. But comparing actual performance to exaggerated claims misses the more relevant comparison, which is actual performance versus what would have been achieved with alternative approaches. The Norden Bombsight, even with its limitations, enabled bombing accuracy that exceeded earlier methods. Whether that accuracy justified the program's cost and the casualties suffered by bomber crews remains debatable, but the instrument did provide genuine capability improvement. The field modifications that mechanics performed contributed to that capability by keeping more bomb sites operational than official maintenance procedures would have permitted. This didn't transform mediocre accuracy into excellent accuracy, but it prevented mediocre accuracy from degrading further due to equipment failures. In aggregate warfare, where success often depends on accumulating marginal advantages, maintaining capability matters even when that capability isn't decisive in individual engagements. The final missions using Norden bombsights in World War II were the atomic bomb attacks on Hiroshima and Nagasaki in August 1945. The B-29 Superfortress, Enola Gay and Bockscar both used specially modified Norden bombsights to aim their nuclear weapons. Major Thomas Ferriby, bombardier on Enola Gay, placed his bomb approximately 800 feet from the intended aim point at Hiroshima. Captain Kermit Beahan, bombardier on Bockscar, placed his bomb approximately 1,500 feet from the intended aim point at Nagasaki. Both were considered successful attacks despite missing their precise aim points because the destructive radius of nuclear weapons rendered such precision unnecessary. The irony was profound. The Norden bombsight had been developed to enable precision bombing that would minimize civilian casualties by hitting military and industrial targets specifically. Its final significant use was to aim weapons that would kill tens of thousands of civilians in single attacks, where precision made little difference to the outcome. The atomic bombings highlighted the fundamental limitations of trying to make war more humane through precision technology. The Norden bombsight enabled more accurate bomb placement, but accuracy didn't fundamentally change the nature of strategic bombing, which remained an attempt to destroy enemy industrial capacity and military infrastructure in ways that inevitably killed civilians. Precision weapons made planners feel better about the moral implications of their decisions, but the results on the ground were similar to less precise methods. The mechanics who maintained Norden bombsights rarely engaged with these larger questions. Their focus was practical and immediate, keeping equipment functional so that crews could complete their missions and return safely. Whether those missions were strategically wise, morally justified, or tactically effective was above their level of responsibility. They fixed bomb sites. What happened after the bombs left the aircraft was someone else's problem, but the separation between technical work and its consequences was never complete. Mechanics knew that the bomb sites they repaired would be used to drop explosive and incendiary weapons on cities where civilians lived. They knew that some bombers wouldn't return. They knew that the entire strategic bombing campaign was contested both in terms of military effectiveness and moral justification. Most lived with these contradictions by focusing on the immediate and controllable. They couldn't change grand strategy or military doctrine. They could fix damaged bearings, replace broken wires, calibrate gyroscopes. So they did that work as well as they could, and left the larger questions to historians and ethicists. Strategic bombing's impact became clear. The moral questions became harder to avoid. The United States Strategic Bombing Survey documented that German industrial production had actually increased through 1944 despite the bombing campaign, suggesting that the strategic effect was less than claimed. The survey also documented the civilian casualties, the destruction of historic cities, the questionable military value of many target selections. The mechanics who'd kept the bomb sites functional weren't responsible for targeting decisions or strategic planning, but they'd been essential enablers of a campaign that remained morally ambiguous. Their skill and dedication had made the strategic bombing campaign more effective than it would have been with less capable equipment maintenance. Whether that effectiveness served a just cause, saved lives by shortening the war, or simply multiplied destruction without changing outcomes remained unresolved. Michael Halloran, in his later years, was interviewed by a local Providence newspaper about his war service. The interview focused on his technical work, the challenges of maintaining complex equipment in combat conditions, the satisfaction of knowing that his repairs contributed to mission success. The interviewer asked whether he'd ever questioned the larger purpose of strategic bombing. Halloran's response reflected the perspective of many who'd served in similar roles. "We didn't have time to question. We had jobs to do, and men depending on us to do them well. The bombers were flying missions whether the bomb sites worked or not. If they didn't work, the bombs would land randomly, which didn't seem better than landing accurately. So we fixed them. That was our war." This pragmatic view characterized most post-war reflections by mechanics and technicians. They'd done essential work under difficult conditions, using skills and initiative that official procedures didn't account for. Whether the larger strategic framework was justified remained a separate question that they generally chose not to engage. The Norden Bombsight remained in military service long after World War II ended. During the Korean War, B-29 seconds equipped with Nordens flew bombing missions against North Korean targets. The instruments proved difficult to return to operational status after years in storage, requiring retired World War II mechanics to be recalled to service because current personnel lacked the necessary expertise. This highlighted the extent to which operational knowledge about the Norden bombsight had resided with individual mechanics rather than in official documentation. The technical manuals described ideal procedures. The actual procedures that made the instruments work in practice existed primarily in the memories of men who'd learned through experience and necessity during the war. During the Vietnam War, the Navy used Norden bombsights one final time for Operation Igloo White, dropping seismic sensors along the Ho Chi Minh Trail. Again, retired World War II technicians had to be called upon because the instruments were too complex and too poorly documented for newer mechanics to maintain using only the official manuals. By the 1970s, the Norden bombsight was finally fully obsolete, replaced by radar bombing systems, laser-guided weapons, and eventually GPS-guided munitions. The mechanical analog computer that had seemed miraculous in 1943 was hopelessly primitive compared to electronic systems that could adjust aim points in real time based on multiple sensor inputs. The surviving instruments were dispersed to museums, where they serve as historical artifacts rather than functional technology. Visitors can see the complex mechanical internals, the precision gearing, the gyroscope assemblies. What they can't see is the history of field modifications, the unauthorized repairs, the hand-lapped bearings and mixed components that characterized most operational units. Museum curators generally restore instruments to factory original specifications when possible, removing later modifications and replacements. This makes sense from a historical preservation perspective, presenting the instrument as its designers intended. But it also erases the operational history, the evidence of how the instrument actually functioned in combat rather than in testing facilities. A few museums have attempted to document this operational history through oral history interviews with mechanics and bombardiers. These interviews reveal the extent of field modifications and the gap between official procedures and actual practices. But the interviews are necessarily incomplete, conducted decades after the events with aging veterans whose memories have faded. The complete story of how Norden bombsights actually functioned in World War II will never be fully recovered. Too much knowledge existed only in oral tradition among mechanics who are now gone. Too many repairs were deliberately undocumented to avoid regulatory problems. Too many modifications were performed under conditions where record-keeping seemed less important than keeping aircraft operational. What remains is a fragmentary picture, enough to understand that field modifications were widespread and essential, but not enough to fully reconstruct the techniques or assess their aggregate impact on bombing accuracy and mission effectiveness. The forbidden fixes remain partially hidden, acknowledged in principle but obscured in detail. This partial obscurity raises questions about how military history should be written and what lessons should be drawn from it. The official history emphasizes equipment specifications, production numbers, and measurable outcomes. The operational reality included improvisation, regulation violations, and informal expertise that enabled the equipment to function despite specifications that didn't account for combat conditions. Both versions are true. The Norden bombsight was a triumph of precision mechanical engineering that represented cutting-edge technology for its era. It was also a maintenance nightmare that required extensive, unauthorized modifications to remain operational in combat. These facts don't contradict each other. They describe different aspects of the same reality. Understanding this complexity matters for contemporary defense acquisition and technology development. Modern military equipment is dramatically more capable than World War II technology, but it also tends to be more complex, more dependent on specialized maintenance, and more vulnerable to failures when operating conditions exceed design specifications. The F-35 fighter aircraft, for example, has sophisticated self-diagnostic systems and was designed for high reliability. In practice, it requires extensive maintenance support and has experienced numerous problems when deployed to forward locations where facilities and parts availability don't match design assumptions. Modern mechanics face similar challenges to their World War II predecessors, trying to keep complex equipment operational under conditions that designers didn't fully anticipate. The tension between configuration control and operational necessity hasn't disappeared. It's been managed through better supply chains, more comprehensive technical documentation, and explicit procedures for field-level repairs. But the fundamental problem remains. Complex equipment fails in complex ways, and the people closest to the equipment often understand what needs to be done better than distant engineers or regulations written for ideal conditions. The lesson from the Norden bombsight's operational history isn't that regulations should be ignored or that unauthorized modifications are always justified. The lesson is that any complex system operating under stress will require adaptive responses that official procedures can't fully prescribe. Organizations need to acknowledge this reality and create frameworks that allow controlled adaptation rather than forcing adaptation to occur through unofficial channels. Military organizations have gradually moved in this direction, incorporating field feedback into design processes, creating rapid modification programs, and allowing more flexibility in field-level maintenance. But the cultural tension remains between the need for standardization and the need for adaptation. The story of Tech Sergeant Michael Halloran and serial number M7432 represents this tension in microcosm. On September 14, 1943, Halloran faced a choice between following regulations that would have grounded an aircraft or violating those regulations to keep the aircraft operational. He chose operational effectiveness over regulatory compliance, using skills and judgment that no manual could capture. That choice was replicated thousands of times by mechanics across the war, each instance small and unremarkable in itself, collectively essential to sustaining operations. The aggregate effect was significant even though individual contributions can't be precisely measured. The strategic bombing campaign's effectiveness, whatever its ultimate value, depended on these countless small acts of technical improvisation. The forbidden fix that made the Norden Bombsight hit targets from 20,000 feet wasn't a single dramatic innovation. It was thousands of small repairs, adjustments, and modifications performed by mechanics who understood that perfect adherence to specifications mattered less than functional equipment when crews were flying missions into hostile territory. September 15, 1943. Lieutenant Morrison's B-17 returned from Frankfurt with all crew members intact. Serial number M7432 had functioned perfectly throughout the mission, maintaining stabilization through flak and turbulence, enabling accurate bomb placement on industrial targets that strategic planners had designated as essential to degrading German war production. Morrison never learned the specific details of how his bombsight had been repaired. He didn't need to know. What he needed was equipment that worked when his life and his crew's lives depended on it. Tech Sergeant Halloran had provided that. The method mattered less than the result. Halloran returned to the bombsight shop after Morrison's aircraft landed, ready to begin work on the next damaged unit. There would always be another damaged unit. Combat operations guaranteed it, and there would always be mechanics willing to do whatever was necessary to keep the equipment functional, regulations notwithstanding. Up next, you've got 2 more standout stories right on your screen. If this one hits the mark, you won't want to pass these up. Just click and check them out. And don't forget to like, subscribe, and turn on the notification bell so you don't miss any upload from us.